started off our unit on EMR some time ago now, and when we did, we talked about, first of all, what causes EMR and what makes up EMR. There's three words that I want you to think of when you think of electromagnetic radiation, just generally electromagnetic radiation. One is electric field. Okay, electric field. EMR consists of an electric field. It also consists of a magnetic field. Electric field, magnetic field, and the third thing that I want you to remember here, I mean, there's lots of little things, right? The idea of sinusoidal waves and so on, but if you can remember three terms, electric field, magnetic field, and one more word that's really, really important, perpendicular. And why do I want you to remember that word? Because everything, if I could just learn to spell it, everything in electromagnetic radiation, if there's a direction, it's perpendicular, 90 degrees. Okay, if I have an electric field wave that looks like this, and a magnetic field wave that looks like this, okay, they're perpendicular to each other. If I have an electric field wave that's on the x-axis and a magnetic field wave that's on the z-axis, then they're going to travel perpendicular to both of those waves. So you've got three things: the electric field, the magnetic field, and the direction of propagation. Everything is perpendicular to each other. Everything is 90 degrees to each other. If you ever get a question, other than like a refraction type problem, right, where the angle could be 37 degrees, you ever get a question that's generally electromagnetic radiation that wants you to talk about direction of something, the answer is perpendicular. Okay, the answer is 90 degrees every time. Now, what causes this electric field, and what causes this magnetic field, and what causes this electromagnetic radiation to travel perpendicular to both of those waves? Who knows the answer to that question? Yep. Good. Not just protons, it could be electrons, any charge, the acceleration of a charge. I'm going to create a little table for you to do a little comparison between a couple things that we've done this year in this unit and in other units. Let's say we've got a stationary charge. Okay, so that's a charged particle. It could be positive, it could be negative, it doesn't matter. A stationary charge is not moving. We've also got a moving charge. Let's say it's moving at a constant velocity, though. And we've got an accelerating charge. We want to know what it produces. Does it produce an electric field? Does it produce a magnetic field? Does it produce electromagnetic radiation? Does a stationary charge produce an electric field? Yes. Does it produce a magnetic field? No. Does it produce EMR? Well, you can't have EMR unless you've got an electric field and a magnetic field. So the answer to that is no. Does a moving charge produce an electric field? Charges produce electric fields, no matter what. Does a moving charge produce a magnetic field? Yes. Does a moving charge produce EMR? A moving charge produces a constant electric field and a constant magnetic field, but that's not what we need. We need a changing electric and magnetic field to have EMR. So it doesn't produce EMR. What about an accelerating charge? Well, that produces an electric field, and it's a changing electric field. And it also produces a magnetic field, and it's a changing magnetic field. Does it produce EMR? Yes, because it produces a changing electric and changing magnetic field. The whole deal, right, with that is changing electric field produces changing magnetic produces changing electric produces changing magnetic, and so on. It becomes perpetuating, right? Perpendicular to each other, perpendicular to the direction of motion. We talked about the wave properties of EMR. Refraction. We talked about that in quite a bit of detail, and we'll go back to that in a little while here. Refraction is the bending of a wave. Waves refract. So does light. So light must be a wave. Diffraction and interference. We'll go back to that and review it as well. Diffraction, interference, the spreading out of a wave, the interference pattern, bright spot, dark spot, bright spot, dark spot. It's a property of a wave. It's exhibited by EMR. Polarization. That's the one that was brand new to us this year. The filtering out of components. If you've got a polarizing filter that's aligned vertically like this, and you've got a vertical wave like this, it'll go through. If you've got a horizontal wave like this, it won't go through the vertical polarizing filter. It's polarized vertically. What if you had a wave like this that goes at 45 degrees? Like this. Would it go through this? Well, the y component of it would, right? The x component would not. It's polarized vertically. So in other words, you find that some of the wave would go through and some of the wave would not go through. Does that make sense? What kind of question are we going to get with that, right? Maybe it says the following properties that are exhibited by EMR show or demonstrate evidence to support the wave theory of light. Refraction, photoelectric effect, polarization. Is that right? No. Photoelectric effect doesn't demonstrate the wave nature of light. Refraction, diffraction, polarization. Is that correct? Yeah, it demonstrates the wave nature of light. This page that you see up on the board right now, what we've seen up here, and including what you're about to see with Hertz's spark gap apparatus here, okay, this page is basically remember a few things. Okay, remember a few things. Associate the word perpendicular with the electric and magnetic field. Remember that moving particles produce electric and magnetic fields, but not EMR unless they're accelerating, and so on. Okay, first couple pages, in fact, are like that. And then we get into okay, now we got to think hard about doing things, lenses, mirrors, and solving all those problems. You gotta just remember this page. What's left to remember on this page? The detection of EMR. Remember, Hertz had the spark gap apparatus. Remember, he had the antenna. Detected a current. And what did that mean? If there was a current produced, then that must mean that there was an electric field and a magnetic field changing, because that's the only way you're going to get a current in the antenna. The antenna is a conductor. Okay, if there's a changing electric and magnetic field, it's going to generate a current in it. Well, what caused the changing electric and magnetic field? It must have been the accelerating charge as it jumped across that gap. So Hertz reasoned that Maxwell's theory must be correct. The accelerating charge caused a current in the antenna, so the accelerating charge must have caused a changing electric and magnetic field, which is exactly what Maxwell said that it should do. Again, this page, not a whole lot of understanding that you need to have for this. For this page, you got to remember some things, okay? And associate words with things, okay? Okay, like some things have got to be automatic. Right? In elementary school, you learn that 7 plus 2 is 9. Okay, you don't stop and figure out every time you have a question, 7 plus 2 is 9, right? You just remember 7 plus 2 is 9. Now, it's important to understand why 7 plus 2 is 9. Right? It's important to understand that. But you just got to know certain things too. You just got to remember certain things. And this page is that. As is this page. We have our spectrum here, where we have all of these types of EMR, radio waves, microwaves, and you guys are definitely going to remember the order of these, infrared, visible light, which, by the way, is made up of all the different colors of the rainbow, red, orange, yellow, green, blue, indigo, and violet. The other ones, by the way, have subcategories as well, but visible light is certainly the most common one that we see with all the different colors. Now we have ultraviolet, we have X-rays, we have gamma. We need to know what causes each of these. Well, radio waves and microwaves produced by oscillating electric charge. Electric charge going back and forth, back and forth. Remember it. Just remember it. Okay, if right now, if 30 seconds ago you didn't remember that radio waves and microwaves are produced by oscillating electric charge and electric current going back and forth, you've got to study a little bit harder to remember that. Okay, it's as simple as that. Infrared, visible light, and ultraviolet, all produced by electron transitions. Picture it. An electron is on the 5th level, and it goes down to the 2nd level. As it does that, it gives off this flash of light. It gives off visible light or infrared or ultraviolet. X-rays produced by rapidly decelerating electrons. I mean, sure, I want you to understand that. I want you to understand that the kinetic energy of the electron gets transformed into photon energy. But when it comes down to it, you've got to just remember as well that rapidly decelerating electrons cause X-rays. By the way, you had a question on your assignment, I think it was question number 7, where you were asked to calculate the frequency of a photon, of an X-ray photon generated. You guys remember that? Vaguely? What do you got there? What do you start with? Okay. It said, in that question, I think it said, the kinetic energy of the electron is whatever it was. What's the frequency of the photon? We start with kinetic energy. It gets transformed into photon energy. Look, that's all you do. Kinetic energy becomes light energy. In fact, in that question, they made it even easier because they gave you the value of 1/2 mv squared. I don't remember what it was, but they gave you EK. They give you the value of the kinetic energy of the electron, and we know that gets transformed into light energy of a photon. So let's set that energy equal to h times f. Or if you were looking for the wavelength of the photon of X-ray, then we'd set it equal to hc over lambda. That's one that you do have, that's a little bit beyond a memorization, right? Okay, remembering that it's rapidly decelerating electrons cause X-rays is memorization. Doing what we just did is a little bit beyond that. Okay, but it comes from the memorized fact that decelerating electrons cause X-rays. Yep. Well, oscillating charge is electrons or whatever charge going back and forth. And transitions, electron transitions in atoms are electrons starting at high levels and falling down to lower levels of the atom. So they might be on the 5th level of the atom, 5th orbital, and then they go down to the 2nd. As they do that, they give off a photon of something. Gamma rays are produced by nuclear decay. Radioactive decay. Radioactivity. When matter changes to energy. And we'll talk about that in a lot more detail in our next unit. Now, we got to be able to identify these, right? In the order that they appear. If I give you a question that says, rank them in terms of increasing frequency, radio waves, microwaves, and so on. If I give you a question that says, rank them in terms of increasing wavelength, then it would be gamma rays, X-rays, UV. It's backwards, right? Because wavelength and frequency are inversely related. If I said rank them in terms of decreasing frequency, gamma rays, X-rays, and so on, you will almost certainly get that question where you have to rank them in order. Almost for sure. What I want you to do, if it's increasing frequency or increasing energy, is just do it in the order that we did it. If it's increasing wavelength or decreasing frequency or something like that, don't memorize or don't try to write them down backwards. Write it down forwards and then read them backwards. Rank them in terms of increasing wavelength. Don't memorize that. Memorize this and then read it backwards. Gamma rays, X-rays, UV, visible light, infrared, microwave, radio waves. It's kind of like the alphabet, right? Okay, if somebody says, recite the alphabet backwards, Okay, that's hard to do out of your head. What's the easiest way to do that? Write it down forwards and then read it backwards, because then it's easy, right? If you have to read it backwards, that's easy. Do the same thing here if you have to rank them backwards. Now, we don't see this very often, but from time to time, we do have to be able to identify, given a certain frequency, given a certain wavelength, given a certain energy, we do have to identify what type we have. So here's what I want you to do. Remember, for frequency, that microwaves are 10 to the 9 to 10 to the 12 hertz. Remember that visible light is 4 times 10 to the 14 to 7.5 times 10 to the 14 hertz. And remember that X-rays are 10 to the 17 to 10 to the 20, was it? Hertz. If it's 10 to the 22, it's gamma rays. If it's 10 to the 13, it's infrared. If it's 10 to the 11, it's microwaves. Now, if you're given a wavelength, we also have to be able to identify it, but my suggestion for that, remember, was just to say lambda is equal to V over F. It's the wave equation, right? Whoops. Change the order of that though, rearrange it. F is equal to V over lambda. So you got wavelength, just solve for frequency. And then you got a problem like you'd have it there in blue. Just compare the frequencies. By the way, what's the value of V? Doesn't matter what kind of EMR we have, radio waves right through gamma rays, 3 times 10 to the 8. What if we have an energy given to us? E is equal to H times F. Solve for frequency. And then compare it against the 3 known ranges of frequencies. 21 different things here, 3 things that we got to memorize. Okay, figure out the rest. There's a question on tomorrow's test, or on Wednesday's test. I'll tell you right now. You got to combine a couple of things that we just did. Okay, you've got to recognize. If I tell you that you've got a type of EMR produced by rapidly decelerating electrons, if I tell you that you've got thermal energy, which is infrared, right? Thermal energy, infrared. Okay, if I tell you you've got some mechanism for production, nuclear decay, radioactive decay, for a type of EMR, or for 4 or 5 different types of EMR, and then I say rank them, then you've got to go through this process of figuring out what type of EMR you have, and then once you figure out what type you have, then you got to rank them in terms of increasing frequency or increasing wavelength or whatever. It's not that crazy hard. It's just a couple of things together there. Do one at a time. Figure out what kind you have first, and then once you know what kind you have, write down the order of the spectrum and figure out what order they should go in. All right. There's the 2 pages of remembering. Again, we want you to understand everything, but for the most part, you got to remember that. Next, we talked about the speed of light. And I changed the order of this ever so slightly here. Our speed of light problems when we did this in class came last, but in the end, I'm going to go through that first here because it's really easy. We use V equals D over T, and we use V is equal to F times lambda. We had one of these questions on our assignment. It was the last question. I think the distance from Earth to this satellite was 20,000 kilometers or something like that. You guys remember that? We wanted to find out how long it took. All we're going to do is say V equals D over T. We know the distance. We know the speed. What's the speed of the EMR? 3 times 10 to the 8. We know the distance. We know the speed. Solve for the time. That's it. Maybe you're asked to solve for wavelength. Well, then take the speed and the frequency and solve for wavelength. Maybe you got to, oh, this would be a tough one. Can you sense the sarcasm? Maybe you need to find speed using D over T and then plug speed into this equation to solve for the wavelength given the frequency, or solve for frequency given the wavelength. Okay. Pretty sure there's one of those on your test tomorrow as well. Test on Wednesday, I mean, as well. Galileo Experiment, honestly, know the gist of that, but that doesn't appear very often. The reason we talk about the Galileo experiment is to recognize why the Mickelson experiment was so much better, right? Why it was so good. You have to recognize sometimes what's bad to recognize what's good. Galileo experiment, remember, 2 hills a kilometer apart. Shine light, bounces, or shine light from the first hill when we uncover a lantern. Okay, uncover the lantern on the second hill when we see it. Time it. What was the big problem with that, though? Yeah, it's reaction time, right? And when we went to the Mickelson experiment, and the big thing with this is that we didn't have the reaction time, right? We eliminated the reaction time. And that's why it was so much better, because we didn't have the human reaction time. How could you make, we start with Galileo, right? Small distance, ridiculously large reaction time. If we can increase the distance, well, that's going to make it better. But it's not going to make it great. Okay, what makes it like so much better is eliminating that reaction time. Increase the distance, decrease the reaction time, and that's going to help. Now, the Mickelson experiment, we are going to see a question on your test on the Mickelson experiment. We know this, right? I told you would. I'm telling you right now you will. Okay, and you're probably going to see it on your diploma exam as well. And the good news is, you saw one on your assignment as well, right? The good news is, it's going to be pretty much the same every time you see it. Okay, I got to cover this up because the answer's there. But there's the question. It looks virtually identical to the one you had on your assignment. Okay, numbers may be different, whatever. This is numeric response. I think on the assignment it was multiple choice, wasn't it? I think on your assignment it was multiple choice. Yeah. But in the end, it's. Oh, look at that. In the end, when we're solving these problems, and when you solve this problem on Wednesday's test, when you solve this problem, probably on your diploma exam as well, you must start out like this. V equals D over T. And T is equal to 1 over F. Now, light travels from the rotating mirror to the mirror on 35 kilometers away and then back again. Okay, that travels a distance twice the separation distance. So you got to be careful to double that distance, and you got to be careful to be in meters. You got to remember that this time represents the time for 1/8 of a rotation or 1/12 of a rotation, however many sides the mirror has. This would be the time for one complete revolution. You will be asked to solve probably for frequency or speed. It is conceivable that you could be asked to solve for the distance that separates them. Okay, in the end, whatever you're asked to solve for, the first thing you're going to get is either big T or little t. And when you get one of those times, I want you to get the other one. If you get little t first, get big T by multiplying by 8. If you get big T, then I want you to get little t, and you're going to do that by dividing by 8. And then plug in your numbers and get something else. Get whatever it is that you're looking for. Okay, somebody in my last class made a really good point on this. If you happen to solve for D, understand that when you get this D right here, it will be the return distance, right? What do you got to do if you want the separation distance? Then you have to divide by 2, right? Okay. This D is, I'm not going to put that in there actually. I'm going to write this D as the return distance. So if you're given the one-way distance, double it. If you're solving for D and you want the one-way distance, then cut it in half. Okay, it doesn't happen very often that we're looking for D. It's very rare. I could probably count on 1 or 2 fingers how many times I've seen a question like that. Maybe even less. Okay. Yeah, 1 or 2 times maybe at most. Honestly, I don't even remember a time when we've been asked to solve for D, but it's certainly something you could be asked for. So we may have seen it 7 years ago. I don't remember. Not recently though. It doesn't make it any harder though, right? You got 2 equations. You're going to plug in numbers and solve for either big T or little t. Get the other one. And then sub it into the other equation and get what you're looking for. Done. Boy, this is about the easiest thing ever. Law of reflection. There's our normal line. Theta I equals theta R. You know what? We got to know this, but we're not going to see this very much because it's so basic. They tend not to ask you those really, really basic questions. If they do, just accept the gift, answer it correctly, and move on. Here's where it gets a little bit harder. This is where people started getting confused with the diagram, the ray diagrams and the calculations and the sign conventions. I want to change this around a little bit. Okay, I want to do mirrors and lenses together this time. Okay, I want to start off with converging mirrors, and over here, converging lenses. I want to draw ray diagrams for each of the scenarios, and I want you to see the patterns that start forming here. Okay, we can see these patterns now. We can see the bigger picture because we've gone through both lenses and mirrors. If we have a converging mirror, by the way, this little notation here, you see this in question number 1 on your assignment, right? That just means it's the back of the mirror, the non-reflecting side. The flat side or the smooth side is the reflecting side. That's a converging mirror. This is a converging lens. Okay, F and 2F. We're going to put our object in both cases beyond 2F. So out here. First ray goes parallel to the principal axis down through the focal point. Second ray goes down through the focal point, parallel to the principal axis. This is where our image is formed. We're going to put our object over here for the lens beyond 2F. First ray to the middle of the lens, down through the focal point. Second ray down through the optical center, goes down through there. What do you notice about both of these images? They are both real. Solid lines intersect. They are both inverted. And they are both, it's a little hard to tell on this one because I haven't drawn it with a ruler. But I think you can see, they're both smaller. If you have a converging anything and your object is placed beyond twice the focal length, your characteristics will be that it is smaller, inverted, and real. Every time. Now, what's the one difference? A real image on a mirror is on the same side of the mirror as the object is. A real image on a lens is on the opposite side. So maybe you get a question sometime that tells you a real image is produced on the opposite side. Is it a lens or a mirror? Think back to your ray diagrams, or remember that if it's on the opposite side and it's real, it's got to be a lens. Let's look at our next possibility here. This time we're going to put our object at 2F. So our object is going to go out here. First ray, parallel down through the focal point. Second ray down through the focal point, parallel. Our image is formed right here. First ray, parallel down through the focal point, down through the optical center. Any notice about this one? The image is real again. It's inverted, and it's the same size in both cases. So if you've got a converging anything and it's placed at 2F, then it's going to be real, inverted, and same size. I'm going to put a star by this one. Some people like to memorize these patterns here. Some people like to sketch the ray diagrams. This is one that I would be familiar with just memorized, because when you sketch this one, it's so easy to be off on that one. It's so difficult to get the exact image that you're supposed to get. You draw that ray diagram, you draw it well, and it just doesn't work out. So I'd remember that one. The other ones you can remember as well, or you can sketch them, whatever works best for you. All right. Next we've got, we're going to put an object in between F and 2F. We'll do the same thing with my converging lens over here. First ray down through the focal point, second ray down through the focal point. Parallel through the focal point, down through the optical center. In both cases, we have an image produced that is real, inverted, and larger. Notice we're going from all three cases so far: real, inverted. We're going from smaller to same size to larger. And notice once again, the real image is formed on the same side of the mirror as the object, opposite side of the mirror of the image. Now we've got one situation where the object is at the focal length, at the focal point. For the mirror, it's a little bit different of a diagram here. First ray is easy. Second ray, away from the center of curvature, back down. They don't intersect anywhere. What about these ones? They don't intersect anywhere either. What do we know about this image? There is no image. Yeah, I'll be honest with you here. We should know how to draw all the ray diagrams. But if you don't like this one, and a lot of people don't like this one, you sketch a converging lens, and guess what? You get the characteristics, right? You see that it's no image, because the image that you get from converging is exactly the same as it is. Converging lens is exactly the same as it is for converging mirror. And the last possibility here for converging this time we're going to make our object really, really close. Here's F and 2F. Once again, F and 2F. This time we're going to put our object in here. First ray down through the focal point. Second ray away from the center of curvature, back upon itself. There's our image. What do you think we're going to get here? There's our image. In both cases, we get larger, upright, and real. I'm sorry, not real. Virtual. We know it's virtual because dotted lines are intersecting there. So converging anything produces the same images. You can memorize that if you want, or you can sketch it. For me, personally, I'd rather sketch it, except for that second one when we're at 2F, because that's the one that you can mess up on pretty easily. The other ones, I'd rather sketch it. But if you'd rather remember them, you go ahead and remember them. Now, pay attention to signs as well, signs of things. Here we'd say that the DO is always positive, right? We'd say that DI is positive. We'd say that HI is negative. F is positive because it's real focal point. This one we'd say that, we'd also say that M is 0 point something. Because it's a real image. When it's a real image, and it is in both cases, then we'd say DI is positive. What do we say here? DI is positive because it's a real image. HI is negative because it's upside down. M is exactly 1 because the image is the same size as the object. Here we'd say DI is positive again because it's a real image. HI is negative because it's upside down. M is greater than 1. 1.5, 9.7, 40. MI is greater than 1. There are no characteristics for this one. And for this one, we'd say, what? DI is negative because it's a virtual image. F is still positive because it's a real focal point. We'd say that HI is positive, and we'd say that M is greater than 1. Now, for this last page, good news is I'm not going to draw another 10 ray diagrams here. I'm going to draw 2. For this last one, we're dealing with diverging. Right, on the last page, it was converging. Here, it's diverging. Here, it's a diverging mirror and a diverging lens. And it doesn't matter where we put our object for these because the characteristics are always the same. These are ones because there's only basically one possible scenario for all 10 diagrams. These are ones that I might invest a little bit of time in remembering. Here's my diverging mirror. Here's my diverging lens. I'm going to put my object wherever. It doesn't matter where I put it because in the end, the first ray will go away from the focal point. Second ray goes toward the focal point and then goes parallel to the principal axis, forming an image right here. First ray goes away from the focal point, which should have another focal point drawn in on this side. Second ray goes down through the optical center like this, forms an image like this. Doesn't matter where you put your object for a diverging lens or a mirror, we will always get a smaller image than the object. It'll always be upright. It'll always be virtual. It'll always be virtual. I'm not good at memorizing things, so I wouldn't memorize all the characteristics of all the different possibilities. But little things like, oh, hey, wait, if I get a virtual image, look, okay, virtual image upright, virtual image upright. Virtual images are always upright. Look at my real images. My real images are always upside down. A couple little things like that might be useful to remember, right? Real images always upside down. Virtual images always right side up. Real images formed on the same side of the mirror as the object. Real images formed on the opposite side of the lens as the object. And of course, virtual images are in reverse to that. So memorize these or do the ray diagrams. But if there's a pattern that you can find somewhere that's quick and easy to remember, then remember it. Yeah, go ahead.
Do we get rulers for this? Do you supply rulers?
If you need one. Yeah, if you need one, I'll give you a ruler. Yeah, for sure. If you need one, yeah.
Do we need one?
I don't think you do. No, I don't think you do for that. So of course we have two equations that go along with this, 1 over dO plus 1 over di for our lens equation, mirror equation, and then of course m is equal to hi over ho equals negative di over do. A big thing for this, really, is remember the sign conventions. Most times the questions are pretty doable if you remember the sign conventions, positive and negative. Remember what's each variable means, like, recognize that it's do, not di, and whatever. You did get one question on your practice test, your assignment. It was pretty challenging, actually. Probably the most challenging one that I've ever seen on the mathematics of lenses. You got, I don't remember what F was. Let's say it was 50. And then you're like, oh, I don't know what DO and DI is. All right. So move on to the next one. Oh, the magnification was, let's say, 20. Oh, I don't remember what DI and DO was. Don't know what they are. How do we do that? You have two equations, same two unknowns. DI is negative 20 times DO. If I took that over there and put it into there, I'd say 1 over 50 is equal to 1 over DO plus 1 over negative 20 DO. Look at that, one unknown. Now, it's still pretty tricky to solve. I'm not going to go any further with that right now. I'll let you do that. But at least it gives you a fighting chance. Somebody in the last class said, yeah, I said, I just actually went through all 4 possibilities and plugged in the numbers into the equations until it worked. Okay. The person said, I know that's not the best way to do it, but it's like, if it works, it works. Right? There's nothing wrong with that if it works. Okay, they give you multiple choice, and usually you can't get away with something like that, but if you can, go ahead. Yeah. All right, next we moved on to refraction. Now, I mean, in the end, when we're doing lenses, we're really doing refraction, right? But we didn't have to do Snell's law or anything like that. Index refraction, remember, is just basically a measurement of how much light bends. We say that n is equal to c over v. C will always be 3 times 10 to the 8. V will always be less than 3 times 10 to the 8. I got my alligator mouth mixed up there. Less than 3 times 10 to the 8. So in other words, you're going to get an index of refraction always that is greater than or equal to 1. It will never be less than 1 because that denominator will always be either equal to 3 times 10 to the 8 or smaller than 3 times 10 to the 8. Okay, that's a good little equation to have, and unfortunately that one doesn't appear on our data sheet. It's never necessary, but it's often useful. With Snell's law, this one does appear on our data sheet. We say sine theta 1 over sine theta 2 equals V1 over V2 equals lambda 1 over lambda 2 equals N2 over N1. This one does appear on our data sheet. Yeah, go ahead. We'll go back to that in a second here. Yeah. We learned as we were going through this that when you went from one medium to the other and N went up, we found that everything else goes down. V goes down, lambda goes down, theta goes down. And of course, if N went down, then you can imagine what happens, right? V goes up, lambda goes up, theta goes up. When you have a prism and white light goes through that prism, now that's not really white, it's more black. But let's pretend it's white light. We see that the glass or whatever the prism is made of has a slightly different index of refraction for all the different colors. Now, we see that blue light bent the most. Theta was highest for blue. What does that tell us about the speed? Or sorry, what does that tell us about the index of refraction? Go ahead. What did you? They were selling. First of all, you guys are a basketball team walking through Sears together? Oh. Guys, listen, blue light has a high frequency, right? Blue light, high frequency, high index of refraction. Red light, low frequency, has a low index of refraction. Now I want you to remember this in just a moment, because in just a moment we're going to go through the whole diffraction interference thing. And of course, that ends up producing the exact opposite effect. It's not red light refracting the least, it's red light diffracting the most. One final thing with this, though, total internal reflection, I'll remind you that when we're going from high to low, index of refraction can't go from low to high. And when you're looking for theta c, the critical angle, the angle at which reflection begins to occur, then you're going to set theta 2 equal to 90 degrees and solve for theta c. So use Snell's law and set theta 2 equal to 90 degrees, solve for theta 1. Yep. Now, what if you get a question that says, you might remember the answer to this question. And listen, on a test, if you remember the answer to the question, that's great. If you don't, let's try to figure it out some way. Let's say we've got two scenarios. Light's going from diamond to air, light's going from glass to air. Okay? Are we going to have a bigger critical angle for diamond or a smaller critical angle for diamond? Diamond has a high index of refraction. If there's a high index of refraction, the critical angle will be smaller. Okay, you might remember that because when we did total internal reflection, we talked about the diamond, right? But you don't have to remember that. You don't have to remember the examples we gave you. You can figure them out. High index, lower theta. Or sorry, lower critical angle. Yes, lower theta.
So if it's in a diamond, it'll.
Well, it just means that the critical angle will be smaller, so that you have a greater chance of being larger than the critical angle, and therefore a greater chance of reflecting. More rays of light reflect off of the diamond air boundary than they do the glass air boundary because the critical angle is smaller. Here's the rule of thumb: if you have a big difference in n, okay, you get a small critical angle. If you get a small difference in n, two materials that are close together like water and glass, okay, that's a small difference, 1.33 and 1.50. Then you get a big critical angle. In other words, you're not going to get total internal reflection happen very easily because the critical angle will be so big. Did this, diffraction interference. Okay, I want to compare a couple of things here. One thing that I already drew, this is the prism. Remember, this is not diffraction, this is refraction. But what do we get? Pink Floyd, The Dark Side of the Moon. High index refraction, blue refracts more, red refracts less. If we have a diffraction grading, let's say with just red light, and we get a pattern that looks like this: bright spot, dark spot, bright spot, dark spot, bright spot, dark spot. If we have multiple colors, then we're going to get something that looks like this. This should be white. First, right, this is 1, second, third. This is first, second, third maximum. What do you do with this? You're going to see this on Wednesday's test, by the way. Okay, you get a question that says, here's this color, this color, this color, this color, but here's your information about, I forget what it is, yellow maybe? Orange, something like that. Okay, what do you do? Yeah, or whatever color it is. Pretend the other colors don't exist. So if in this question you were dealing with blue, you would say that red doesn't exist. And look at what you're left with. First order, second order maximum, third order maximum, and so on. Just use your data for whatever color you happen to have. Right? My equations. Oh, notice one thing though. I shouldn't have erased that. One quick little thing here. Red light refracted the least. Red light diffracts the most. And I mean, in the end, when we look at our two equations, lambda is equal to d sine theta over n, and lambda is equal to xd over n times L. You could figure that out, right? If lambda is big, then x will be, no, look, they're linear related, right? If lambda is big, then x will be big. So if lambda is big, red light has a small frequency and a big wavelength, then x is going to be bigger. Red is going to be spread further apart. You could see other relationships here too, right? What happens if I increase the value of little d? Well, if I increase the value of little d, x goes. Now, if I put those on opposite sides, right, rearrange it. If I increase the value of d, x goes down. And if you want to find a relationship between a couple variables, like find an equation and find the relationship. You have to do that as well. This question, what is it on your exam here? Question, yeah, 2 questions here. Get a whole page of information here. Then you get a couple questions that go with it. One of them is a math problem, and then one of them is a relationship problem. Okay, when we change the value of little d, or we change the value of lambda, or we change the value of something, what happens to x or L or whatever the case may be? Remember to use this equation if L is greater than 10 times x. And remember that if it's not greater than 10 times x, we've got to find the value of theta. We can find the value of theta by using the tan function given x and given L, and then we can go back to the other equation. Good?